We're asked to find the mass and the center of mass of a thin plate or a lamina that occupies some domain region that is given by the functions here. Y is equal to square root x, y is equal to 0, and x is equal to 1. We're also told that this plate has a varying density function, meaning that the density is not the same throughout the entire region. So let's begin by graphing this domain region, which is y is equal to square root x is equal to 1, and y is equal to 0, which is the x-axis. So this is our region D here. And this varying density function tells us that as the x values get bigger, the density is increasing. So it is more dense in this region than it is over here. So we begin by finding the total mass of the system. And the formula for determining the total mass is the double integral over this domain region with our varying mass density function, dA. And in this scenario, the varying mass density function is just x, and now we need to determine whether or not we're going to use dx dy as the order of integration or dy dx. So we think about a little floating rectangle within the domain region, and we decide, is it better to float this thing from left to right, or is it better to float this thing up and down? And in this case, it doesn't really matter. If we were to integrate with respect to x first, floating it left and right first, our lower limit is y is equal to the square root of x. We could not have square root x in the limit if we integrate with respect to x, so instead we would need to solve for x by squaring both sides. Y squared is equal to x, and integrating with respect to x first, the lower limit for x would be y squared, and the upper value of x is the constant x is equal to 1. And then in order to get the limits for y, we consider what the y value would be when our band is at the bottom extreme, and when it's all the way down here, the lower value of y is equal to 0, and when the band is at its upper extreme, we get upper limit for y, which is positive 1. So now in order to calculate this integral, we'll look at this first iteration, which is the integral from y squared to 1 of x dx. And since we're integrating with respect to x, we do want to make note that these are x limits. The integral of x with respect to x is x squared over 2, and then we evaluate this from y squared to 1. Let's pull the 1/2 to the outside and plug 1 in for x squared minus y squared in for x squared. And so we get 1/2 times 1 minus y to the 4th power, which becomes the integrand for the second iteration. So now we're looking at the integral from 0 to 1 of, let's pull this 1/2 to the outside. We have 1 minus y to the 4th, and we're integrating with respect to y, which makes these y limits. And this antiderivative is going to be 1/2 constant multiple pulled to the outside times y minus y to the 5th over 5, evaluated from 0 to 1, which gives us 1/2 times, plugging in the upper limit of 1 to the antiderivative, and then from that we subtract the lower limit of 0 plugged into the antiderivative, which then gives us 1/2 times 4/5, which simplifies down to being 2/5. And again, this was the total mass of the system. So we'll make note of that up here and then proceed to find the moment about the x-axis and the moment about the y-axis, which will then enable us to find the center of mass. The formula for calculating the moment about the x-axis is going to be the double integral over this domain region, and the tendency to rotate about the x-axis is going to take into consideration a bunch of distances from the x-axis, which are y-coordinates, times the varying mass density function, dA, and this is basically the mass of the little tiny rectangle multiplied by the distance that it is away from the x-axis. And the tendency to rotate about the y-axis is going to be that double integral over the domain region, where we're looking at the mass of the little tiny rectangle, which is mass density times dA, multiplied by the distance that rectangle is away from the y-axis, which is an x-coordinate. So for our scenario, these integrals become y times x dA here, and x times x dA here. Now since this domain region D is the same for all these double integrals, we can use the limits that we've already established, meaning that we'll integrate with respect to x and then with respect to y using the same limits, y squared to 1 and 0 to 1 for both of these double integrals. So let's begin with the moment about the x-axis, looking at that first iteration, which is the integral from y squared to 1 of x times y dx. So again, with respect to x, these are x limits, and the antiderivative is going to be this constant multiple times x squared over 2, with the limits y squared to 1. This y is the constant multiple, and the limits get plugged in for x. So the upper limit of 1 is going to be plugged into the antiderivative, and then the lower limit of y squared gets plugged in to give us y times 1/2 minus y to the 4th over 2, which is the integrand for the second iteration. But I'll distribute in that y to make the integration easier. So the second iteration will be the integral from 0 to 1. Having distributed in that y, we get something that's easier to integrate, and the antiderivative is going to be 1/2 times y squared over 2 minus 1/2 times y to the 6th over 6. And then we apply our limits of integration to all of this, which will basically just be 1/4 with 1 plugged in for y, minus 1/12 with 1 plugged in for y, and then minus 0 with the lower limit plugged in, which simplifies down to being 1/6. So let's make note of that up here and then proceed to find the moment about the y-axis. So the moment about the y is going to be determined by this double integral. So that inside first iteration is going to be the integral from y squared to 1 of x squared evaluated with respect to x first. So this antiderivative is going to be x cubed over 3 evaluated from y squared to 1. So we plug in the upper limit and then subtract the lower limit plugged in, which yields 1/3 minus y to the 6th over 3, which becomes the integrand for the second iteration, which is the integral from 0 to 1 of 1/3 minus 1/3 times y to the 6th dy. This antiderivative is going to be 1/3 times y minus 1/3 times y to the 7th over 7, evaluated from 0 to 1. We plug in that upper limit of positive 1, minus plugging in the lower limit of 0 is just going to be 0, which leaves us with this moment about the y-axis being 1/3 minus 1 over 21, which is 2/7. So let's take this moment about the y and pull it up here with everything else. And now we have everything that we need to determine the center of mass for the system. Now remember, the center of mass for a system is going to be an xy ordered pair, where the x-coordinate is going to take into consideration the moment about the y, or the tendency to rotate about the y-axis, divided by the total mass of the system. And the y-coordinate is going to take into consideration the tendency to rotate about the x-axis, and divide that by the total mass of the system. We calculated the tendency to rotate about the y-axis to be 2/7, and the total mass of the system was 2/5, and so the x-coordinate of the center of mass is going to be 5/7. We calculated the tendency to rotate about the x-axis to be 1/6, and again the total mass of the system was 2/5, and so this turns out to be 5/12, and take these together to get the ordered pair 5/7 and 5/12, which is the center of mass of this thin plate. Remember, the plate is more dense as the x values get larger, and our center of mass ordered pair turned out to be 5/7 as the x-coordinate, 5/12 as the y-coordinate, which is fairly close to 1 in the direction of x and fairly close to 1/2 in the direction of y, so about right here. The fulcrum point would need to be here in order to be placed in a spot that supports the majority of the density.